Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture. In the last lecture, we had studied the analysis of block type machine foundations for vertical vibrations and yawning. Today we are going to study the analysis for the combined rocking and sliding. Let us try to understand how the two phenomena, rocking and sliding, occur and how they are coupled. So please take note of the coordinate system. We have the x-axis towards the right and z-axis vertical, and we are drawing the coordinate system through the combined center of gravity G of the machine, the block and the base. So essentially the soil stiffness can be simulated as a combination of a linear spring connected at the base and a rotational spring connected at the center of gravity G. Now it must also be noted that because the y-axis is going inside the plane of the slide of the sheet, so the positive direction for the moment my is basically clockwise. So here we are showing the force Px, which is acting in the positive x direction, and it has a lever arm D from the combined center of gravity G. So the moment my is basically the product of the force with the lever arm D, and here this is the positive sense of the moment being clockwise. So if the foundation system is under pure sliding, then this can be represented diagrammatically like this. So this is the hypothetical case that the foundation system is undergoing pure horizontal displacement under the force, and similarly we can show the hypothetical pure rotation as the block undergoing rotation about the combined center of gravity G. But as we have explained before, the two motions, sliding and rocking, they occur simultaneously. And just like we are showing here the combination of sliding and rocking, the combination of sliding and pitching is also similar. Only difference is that whereas the rocking is happening about the y-axis, pitching occurs about the x-axis. The positive direction of the angle of rotation for rocking is again shown here. So how does the combined action of sliding and rocking work on the machine foundation is shown here. So we can visualize the combined action as a sort of rotation of the entire foundation system about an external point. This external point could be below the foundation or above the foundation. So here we are just showing the combined action about a point which is situated below the foundation. Please note that as far as rocking or pitching is concerned, there are two schools of technical opinion. Let's briefly discuss them here. So according to the book of K.G. Bhatia, the rotation that is in the form of rocking and pitching is modeled so as to be taking place with regard to the center of gravity of the base of the foundation block as it's shown here. So it's assumed that the rotational spring is connected at the base point. But if we go with regard to IS 2974 and also the book of Vaidyanathan, the rotational degree of freedom is assumed to be positioned at the overall CG of the machine, the main block and the base of the foundation system, as is shown at the top diagram. Let us now write the equations governing the combined rocking and sliding for such situation. So we will be deriving the system of equations for the combination of sliding and rocking, and similar derivations can be made when rocking is replaced by pitching. So here we are defining the height of the overall CG from the base of the foundation as S. So if the foundation block undergoes a rotation about the CGG, then what this does is that this leads to a sliding movement equal to S theta y at the base of the foundation. So the equation of motion for the horizontal vibrations can be written like this: m into x double dot, and then when we write the second term, the spring stiffness multiplied by the displacement. So the net displacement at the base of the foundation is x minus s theta y. So the term minus s theta y is on account of the sliding, which is related to the rotation theta y. Let us now formulate the equation for the rotation part. So the first term is phi y multiplied by theta y double dot that is the inertial term, and now we write the stiffness term, the stiffness k theta y, which is the rotational stiffness multiplied by the angular displacement theta y, and then we have on the right hand side the moment. So the first part is my, which is the moment on account of the external load, and because now we have the shear stress acting at the bottom of the foundation on account of the sliding moment, so we have an additional term as shown here. So that is the spring stiffness multiplied by the horizontal displacement, and this is adding to the external moment my. But this is not the end, we have another component which is now shown here. So imagine that the block has undergone rotation about the y-axis as shown here. Then there will be an overturning moment formed by the pair of the weight of the block and the normal reaction as shown here. So the overall weight of the block acts from the overall CG, and then the normal reaction, it acts from the midpoint of the foundation. So the two have a distance equal to s theta y, and how this s theta y comes, so basically it's the tangent of the angle formed by theta y, and assuming that theta y is small, so tangent is taken to be numerically same value as the angular displacement theta y. So this term also needs to be added, so that's the last term. Mg is the weight and s theta y is the separation between the normal reaction and the weight. So now we have the two equations, one for the horizontal vibrations and other for the rotation, and because in the equation for the horizontal motion we have the term theta y, and similarly for the equation concerned with rotation we have the term x. So that's why this is a 2 degree of freedom problem. The two motions, the horizontal sliding and the rotation, are mathematically shown to be coupled. So let's see the solution procedure. We are not deriving the final solution, but we are just writing down the steps involved. So the first step is that we have to obtain the limiting frequencies. By limiting frequencies we mean the hypothetical case of pure sliding and pure rocking. So first of all we assume that the soil has infinite rotational stiffness. So if that is the case, then the system will undergo pure sliding only. And if it undergoes pure sliding, then the equation of the system will be very simple. We will not have the second term in the equation for the horizontal vibrations. So this would be the equation of motion for pure sliding vibrations. So the hypothetical frequency omega xn is called as the limiting frequency for this particular situation. So that's given by the square root of k tau x divided by the overall mass m. Next we assume that the soil has infinite shear stiffness or the sliding stiffness. That means the foundation is unable to undergo any sliding movement and it undergoes pure rotation only. Now it should also be noted here that since sliding is not at all possible, the rotation must occur about the CG of the base of the foundation. Otherwise, if rotation occurs about the overall CG, then some sliding would occur on account of the rotation, as we have seen for the case of the coupled case. So here we are showing the foundation block and it is undergoing rotation about the base of the foundation, and this is because of the infinite sliding stiffness. So here invariably the rotational spring is fixed at the base. As pointed out earlier, S is the height of the overall CG from the base of the foundation. So when the foundation undergoes a rotation theta y about the base, the CG gets drifted to the right by a distance s theta y as shown here. We shall use a symbol G1 to indicate the CG of the base of the foundation system. So for this particular situation, the rocking vibrations can be represented by this equation. So we have the inertial term and the stiffness term, and for the moment, now we have the external moment My, but then there won't be any moment induced by the shear stress. However, the moment induced by the couple formed by the normal reaction and the weight shall be there. And please note that here phi y is replaced by phi y naught. So phi y naught is basically the mass moment of inertia of the entire system with respect to the CG of the base. So now the equation can be written in this form. We are bringing mgs theta y on the left hand side and we are clubbing it with the stiffness. So it is as though the overall stiffness of the system has reduced. So for this particular case, the frequency, which is the limiting frequency for rotation, can be expressed as shown here. It's the under root. So on the numerator we have k theta y minus mgs. So apparently the system stiffness has reduced, and at the bottom we have phi y naught with respect to the base. We define now our parameter alpha y as the ratio of phi y to phi y naught. So phi y is the mass moment of inertia about an axis passing through the overall CG, which is indicated by symbol G. So it's the CG of the machine, the base and the block. Now the next step is that we determine the final coupled natural frequencies. So the computational procedure is as follows, that we define two variables a and b first. So the variable a is basically the sum of squares of the two limiting frequencies, and the term b is 2 under root alpha y multiplied by the two limiting frequencies again. So once we have determined the main constants a and b, the coupled frequencies, they can be expressed as shown here. So please note that the terms here, they are basically expressing square of the coupled frequencies omega n1 and omega n2. So omega n1 is the higher one and omega n2 is the lower one. It should also be noted that these frequencies are the angular frequencies, so they are in radians per second. To convert them into hertz, we need to divide by 2 pi. Now there are two coupled frequencies. This is because there are two modes of vibrations. In one case, it is as though the coupled vibrations are represented in terms of rotation of the entire system about a point located below the foundation block as shown here. So for this, the angular frequency is omega n to the lower one. The point of overall rotation is located at a distance below the CG of the entire system as shown here. So the main parameter here is S. S is the height of the overall CG measured from the base of the foundation system. Similarly, for the other mode of vibration, the center of rotation is located somewhat above the foundation system. So for this particular case, the angular frequency is omega n1 and this is the higher one. Similarly, we can express the height of the center of rotation above the overall CG by this expression. The amplitudes of vibrations can be determined by following expressions. Please note that the values are applicable at the CG of the combined system consisting of the block, the base and the machine. Please also note that two amplitudes need to be evaluated. One is the displacement amplitude and the other is the rotational amplitude. So the displacement amplitude is given by this expression. The expression for the rotational amplitude is as shown here. As a result of the combined vibrations, we need to find out the net amplitude of the horizontal vibrations at the top and the bottom of the foundation block. So at the top of the foundation block, it will be given by the value as shown here. So note that h is the total height of the block. So what we are doing, we are multiplying the rotational amplitude with the height of the top above the G. Similarly, at the bottom, the expression for the amplitude can be written as shown here. So here there will be minus sign. Now this plus and minus has been worked out taking into account the positive direction of the rotation. So we need to check for the limiting values of the displacement at the top and bottom points. So once we have computed the essential parameters, namely the displacement amplitudes and the frequencies, then we can check for the adequacy of the design. So essentially the design inputs which are required are as follows. Number 1, we need the operating frequency of the machine. So this information has to be supplied by the manufacturer. Either it could be in radians per second or in hertz. Next, we also need a layout of the top of the foundation system. Often this is provided by the manufacturer. And also we need the loading diagram consisting of the locations where the forces are acting, their magnitudes and the directions. Most manufacturers, they provide a layout of the top of the foundation block because they would be fixing their machine, so often they specify their requirements in terms of the anchor bolts which should be left over at the top of the foundation, or pockets in the block where the machine can be fixed. So usually these pockets are rectangular in shape. The manufacturer brings the machine and he then places the machine along with the anchor bolts, and then the grouting is done to fill up these pockets. For example, here we are showing a typical sketch of the layout expected by the manufacturer of the machine. So he has also specified that what should be the shape of the top of the concrete. So this shape and the locations of the anchor bolts or the pockets are to be adhered by the structural engineer. Of course, these dimensions are tentative. The planned dimensions are meant to be above the finished ground level or the finished floor level. Once we talk about the region under the top of the soil, then it's up to the structural engineer who can assume appropriate dimensions to match the requirements of the frequency and the amplitude. The next input for the design comes from the geotechnical engineer, and these are the static and the dynamic properties of the soil. So we need allowable net bearing pressure, we need the elastic constants Cz, C theta, C phi and C tau. In addition, if we have the values of the Young's modulus and the Poisson ratio, then that's also desirable. Now the textbook by Vaidyanathan, it suggests some values of the elastic constants of soil in the absence of any tests. Now these values have been taken from the old version of IS 2974. However, in the latest version, the recommendation is that these properties should be determined by elaborate testing. Let us also take note of some of the important points which are applicable for block type foundations. Now it's desirable that the groundwater table should be lower as compared to the bottom of the foundation. The reason is that water is a very good conductor of vibrations. The acceptable guideline is that the distance between the bottom of the foundation block and the water table should be at least 1/4 of the length of the foundation system. However, often we have to do a trade-off because the geotechnical engineering report must be suggesting some minimum depth for the foundation block, and that has to be adhered to. However, in situations where the static load coming from the machine and the block together is low, then the geotechnical report might provide reduced allowable net bearing pressures at shallower depths. In any case, the concurrence of the geotechnical engineer must be taken. Then it's also necessary that hot pipes should be isolated. Then it's also necessary that concrete should be protected by acid resistant coating, because often the operation of the machines might involve releasing chemicals, and these could be detrimental for the concrete as well as for the reinforcement. Some of the chemicals might reinforcement corrosion. Now, in order to make sure that the vibrations are not transferred to the surrounding structure, it's also advisable that the machine foundation should preferably be placed at a level lower than the bottom of the surrounding structure. Now, this provision number 5 may be in conflict with guideline number 1 with regard to the water table. So the engineer has to accept a certain level of trade-off between the two. The stepwise analysis design procedure is as follows. We will be doing a tutorial and shall be solving a problem so as to illustrate all the steps. The very first step is that we have to assume a layout in plan and elevation. As far as the plan dimensions are concerned, we need to adhere to the suggested dimensions by the manufacturer at the top. However, once we are inside the soil, we can choose different dimensions to match the design requirements from structural engineering point of view. So once we have fixed these dimensions, we can easily find out the various geometrical parameters such as the area, the moment of inertia, the mass moment of inertia, and mass, etc. The next step is to determine the CG of the entire system consisting of the machine, the block, and the base foundation. It is desirable that all these CGs must lie in one vertical line and should match with the line of action of the force in the vertical direction. A maximum tolerance of 5% is permitted. Then we should find out the stiffnesses associated with the foundation system for various types of vibrations, the vertical vibrations, the horizontal vibrations, the rotation, etc. Then we find out the natural frequency of vibrations. We have already specified that the vertical vibrations and the yawning are independent, they can be determined independently, and then the rocking and sliding are coupled. So for these we need to first find out the limiting frequencies, and once we have the limiting frequencies, then we can find out the coupled frequencies also. The next step is that we have to determine the displacement amplitudes. Now if the vertical vibrations are happening, then these can be determined independently. Similarly, for the yawning, the amplitudes for horizontal displacements can be determined independently. But if the vibrations are coupled as for sliding and rocking, then we have to use the expressions we have derived in this lecture. Then after the displacements, we need to find out the total pressure under the foundation block, and when we say total pressure, it has to be made up of both the static and the dynamic components. This must be lower than the allowable net bearing pressure. Finally, we have to determine the inertial forces. So for inertial forces, we'll be dealing with a separate lecture, because the machine and the foundation system is undergoing vibrations, so inertial forces could sometimes be very large. Note that if we are not getting the desired results in steps 4 and 5, we need to again revise our sizes. So machine foundation design process is basically iterative in nature. We shall undertake an example of a machine foundation design to strengthen our learning for steps number 1 to 6. We will take up the step number 7, that is calculation of the inertial forces, separately. So thank you very much. If you have any questions, you can discuss them during our interaction in the MS team.